Okay, I think before we start, as I mentioned in the Moodle, and I think some students also mentioned Tuesday class that I think in the feedback questions, I think I have some typo, so I didn't really check the questions. But just to make sure, okay, if I have, for example, y double prime plus, let's say 2y prime equal 3. Let's say that's our equation. Okay. Remember, when we have this double prime, this means it's the order. Okay, this is the order. Okay? So this is second order. And nothing wrong with that with the other components. So we can just say it's linear. Okay, so second order, linear. However, if we, for example, let's say we have dy dx and then equal the, it's still, both are the orders. But if we take this, for example, 5 with power of 5, this becomes nonlinear. This was supposed to be the question, yes, that last Tuesday. I forgot to put the power, so it's only the bracket. Okay, so this is makes nonlinear. Okay, and also the nonlinear also came when we have functions that is when, for example, sine y plus dy over dx equal 4. Now, because y is our dependent variable and it has sign, in our case, in our differential equations, this becomes nonlinear. Okay? Okay, that's just some things that I need to confirm and clarify from the previous questions. And I think the last questions is asking the m is also a typo. It should be, yeah, it's need to switch m and x. Okay, so that's also a typo because you will confuse when you derive. yeah, really sorry about that. Okay, anyway, I want to finish off the topics for today. The autonomous first ODE. Okay, I just want to finish off this a little bit more, and then move on to the next sections, which is the one of the techniques, the separable differential equation. Okay, now we already talked about this. So when we have our autonomous order, so remember, autonomous means that there is only dependent variable y in the equations. Okay? There is no x, or you cannot find the free independent variable inside the equations. Okay? Now, if we take a look at this example, we can make these critical points y equal -1 and y equal 1, and we can draw them. For example, this is just a sampling from the solution. Actually, the solution can be in any as long as it fits the slope field. As long as it fits the slope field, that will be our solution. But this is to show you that at these three regions, let's say the region 1, 2, and 3, you see that it's decreasing and then increasing and then decreasing again, right? Okay. So from that decreasing, increasing, and decreasing again, we can sum up into what we call the phase line. Okay, this is called the phase line. The phase line is actually just to confirm that our critical points, or what's the condition on our critical points. Is it stable? Is it unstable? Or there's one more condition, it's semi-stable. So let me go through that in the next page. So let me just sum up so you can which. So this is example. Okay, this is from the equations. It's from your textbook. It's an example. So this is when you have the, this is for dp over dt is equal p a minus bp. Okay. So you will see that the critical points p equals 0 and p equal a over b. This is the critical points. And if they behave like this phase line here, then we can see the stability of each critical point. Okay. Okay, now the phase line, we may have several or variations throughout the example. So we call this the first one on the left one. It's called the attractor. So it's attract to the point, which means it's stable, asymptotically stable. Stable, or this is attractor. The second one, they both goes away, opposite sides. It's called the repeller, or it's unstable. And it's called the repeller. And C or D, they both goes into the same directions. We call this a semi-stable. Okay, semi-stable. So both this is called the semi-stable. So that's the autonomous differential equation. So in autonomous differential equations, the important thing is to know the critical points and get the conditions, okay? Whether it's stable, it's semi-stable, or it's unstable. Okay. Perhaps you are wondering, how do we use the autonomous differential equation? This can be used in some, I think the application is for some simulations. For example, I believe in statistics, especially for logistics, they will use this kind of autonomous order for first differential equation to predict. So for a prediction, if we know that the critical points will be, this will be stable, then they will predict, they will be, maybe the sales going to be stable, or maybe if you want to correlate with the demand and supply for some products, they can also use this kind of. I think I forgot the name of the formula, but it's something logistic. Okay, if I know, I will maybe describe to you. Okay, but there's some application on logistics. Okay, I think that is autonomous first order. Okay, now next part of the sections, we are still in the first order, and we were going to describe several techniques. Okay, but before I give the method, let's just consider the exponential growth that we are familiar with. Usually we are writing this rate with k and y, right? Of course, if you remember the nature of the exponential, you are going to see that when we have differentials like this, dy over dt, and it goes back through the original equations, you can predict that probably the original function has to do something with the exponent e, right? Because if we derive e, we will have something e, and we have another constant. Okay? It depends on the chain rule of the E if they have functions on the power. Okay? For example, if you have E with power of 2x, then dy over dx, let's say it's going to be 2e 2x. So we have its original equations. So to get to some review, we can start with probably just take integral and then take like this and then try to integrating both sides with both variables. Okay. And we are going to see that this will lead you to the ln, and this will lead you to the just maybe kt, okay, and then let's say a constant here, and we can rewrite this ln with the e, right? We can rewrite with e ln y. It's the same thing, right? And this will be e kt plus c, right? And we can erase the e, right? So we can write down that ln y is kt plus, or e, let me write e for ln y is e kt, and then let me just write with e c. We can write like that, and e with power of c is another constant, so I will just rewrite that as just a constant. So let me write it with just a constant like that. So we know that should be y. Okay, sorry. So we can write this as y is c e kt. This is let me write a bigger c to make it different from the first c. So what we have here is practically we get the e that we predict before. What we did here is we take all the variables to one side and another variable to another side. This is an introduction course how we can use this as a technique to find our solutions. We call this separable differential equation. Separable technique. Well, let me go through what kind of technique is it. Okay, so let me write in a more complete. So consider the first order differential equations. Dy over dx is equal a function. Okay. And f doesn't or maybe let me write a little bit down here. When f doesn't depend on variable y, we will have fx y equal g of x. Okay. Then we can write down that dy over dx becomes this g of x. Okay. Now this part, of course, we can solve this through solve by integration. Can be solved by integrations. So we can solve that, and we are giving that if we want to integrate, we can just integrate g of x dx, and probably this will end up with, let's say, another functions, antiderivative g plus a constant. Okay. Okay, now the question is, what is the requirement for us to make these integrations? Okay. So now this is the notes part. It's called the separable equation. So first order differential equation, dy over dx equal g of x, and also we have h of y, okay, is said to be separable. Let me write more clear. To be separable or have separable variables. So if we look at, for example, like dy over dx, so example, x squared y with power of 4, and then we have an e 5x minus 3y. Can we separate this? I think we can, right? We can by taking this x, or maybe separating this becomes and then we can separate all the x squared e 5x, and then separating this y4 and then e negative 3y. And then by looking at this dy over dx, we can separate this x goes through here, right? And this goes through here. Okay? So it's separable, right? Okay. So whenever you find a product that is having two variables, at least y and x, for example, and you have the function of x and function of y as a product in differential equation, it means that you can separate those variables. Okay, each goes to the each variables, and then you can integrate each components. Okay, that's the idea. Okay. If we have, for example, differential equations that is, let's say, just y plus cos x. Okay. Now this is interesting. We want to separate this y plus cosine x, but the plus signs, it's blocking our separations. Okay. We want to move out to the left, but that will be still, there is a subtraction or addition signs that is, we cannot overcome that differential equation. We cannot separate them, so we need to use another method. Okay, so that is the limitations for separable equation. The techniques is easy. It's just regular integral. Okay? So you need to separate variables, x, y, or any variables you want, and then integrate. Okay, that's the key. Okay, the idea. Let me check the key. Okay. Let's see the other, just a simple equations. So if we have another example here, dy over dx, let's just say it's just xy. To see how we can separate this. So first, take for each variables, okay, and then taking the x dx like that. And then take integrations, both sides. this will be ln, and this will be x squared over 2 plus a constant. Now, if you want to take y, then we will have e x squared over 2. And then this is supposed to be plus c, but let me write e and constant, just skipping some process there. And because this is another constant, we can write that the absolute of y is equal to, let's say it's big C, or maybe change to D to make some difference. Okay. Now, we can make sure that the D is, of course, positive, right? Because of the exponent. And y equals 0 is probably a solution. And because of the absolute value, we can make sure that the answer is, we can just write this y equal d e x squared over 2. And perhaps we need to check. So check. This is to make sure checking the equations, whether it's our solution or not. So we can check, and this will turns out to be just take differentiations. So 2x over 2 is x, so x, and then multiply d x squared over 2, right? And this is our y, right? So this is just x, y. Okay, so we get back to the questions, the DE. So which means that our goal is successfully, it is a success. Yeah. Okay. Perhaps let me just make some general steps here on the right, just to make sure that we know. Okay. So from the beginning, I'm writing this dy over dx, and then having f of x and g of y, and then take integrations, and then integrations, take integrations, and then it's end up with the plus constant. Okay, let me give you maybe one more example, and then we can see the other one. So because we are dealing with some integrations, I hope you still remember some techniques. Okay, some techniques from I think calculus 1. Okay, some integrations. Because I will not be able to cover all the techniques and all the examples. So the other part that might come for some problems, you need to try to remember, okay, try to review. Okay. This is the right part here is just general steps. Okay, general steps for separable equations. Separable equations. Okay, let me give you another example. Okay, solve x squared y prime 1 minus x squared plus y squared. Let's see if we can solve this. It's quite long. I think it's quite difficult. But let's try. Okay, let's try. Just to check whether we are able to do this and review some parts of our calculus. Okay, I think this is quite challenging. I think this is quite challenging, right? Oh, I think I need to give you the easy one first. But let's just try. Okay, let's just try. So from like easy and it's jump really high. So the problem I think here, right? The 1 minus x squared plus y squared minus x squared plus y squared. Can you do something about this right part? Because this is, I think, the essential part is this right side. If you can do something and maybe some manipulation, some rewriting the form and making the form maybe how to separate this x and y, right? That's the important. So usually in the differential equation, if the question is asking like really specific, as you remember, I think from last week, that we need to have the initial bound. This is the initial bound. This is to limit or to restrict which solution we are going to achieve. Because if not, will be many solutions, right? We have family of solutions. So we restrict the solution as this 0, 1. Okay? Or 1, 0, x equal 1, y equal 0. Now, the idea for this right side is to factor first. Anyone got the answer yet? Or maybe trying your best? Let me just show you. So let's say we are going to if we have, this is 1, right? We have 1, we have x squared, we have y squared, and we have both of them. So perhaps this will start it with 1, and this is another 1 to make 1 by 1. And then because it has 1 and minus and plus, probably this is minus and plus here, okay? And then we just to make sure which one is plus, which one is minus. So we can just some trial and error, okay? So from this clue. So the clue is from this 1, okay? And then it has x squared and y squared, and then it has the both forms. So let's say we check the x squared and then y squared like that, okay? We check 1, right? And then minus x squared plus y squared, and then minus x squared y squared. I believe this will be the forms that we are going to look for. And this is separable. We can separate this. So we can write down, or maybe y prime. So first we write on the left maybe this y. Usually y on the left and then x on the right. And after this, then the next problem. Okay, the next problem. After separation, next problem we have is how to integrate it. I hope you still remember how to integrate. I think that the right part is easy. You can separate this 1 over x squared, and then minus 1, right? I think it's easy to be calculated. So the right side we can write as 1 over x squared minus 1, right? We can integrate this easily. But the left part, we have the, let's say this y prime, I will separate also, so dy and then dx goes here to make it easy to follow. So this will be dx. Okay. So let me just write here 1 plus y squared and then dy. So if we integrate this, anyone still remember what integral this is? Yeah. Okay, arctangent inverse. So we can write tangent inverse of y. And this will be negative, right? Should be negative because it's negative 2 plus 1, right? Yeah. And then negative x, and then plus a constant. And since it's tangent inverse, we are going to have y equals something that is the solutions, right? So every differential equations, what we want usually at the end is y equals something or any variables that is in the question. Okay? That is what we want. Okay? So tangent inverse, we need to write in terms of y. So we are going to write tangent of all this. Before we go here, maybe we need to check the constant. That's where the where is it? Here, the initial value. Okay, so initial value. So the next part after we integrate is finding this. Okay, so let me help you to write. So first step is separation. The second step is integration. And then the last part, usually we need to find, compute the constant. Okay, initial conditions is when x, so when x is 1, y is 0. So let's just plug in. So when y is 0, tangent inverse 0 is 0. So we can write 0, negative 1 over 1, negative 1, and then plus a constant. So constant is 2. Okay. So we are going to plus 2 here. So this will be our answer. Okay. Okay. Now, because we are now dealing with the integrals for these techniques. I think I also mentioned that there are several functions that cannot be integrated, right? So the best way we can do if we are encounter that problem is just leave it as the integral defined functions. Okay? So we may have integral defined solution. So the integral defined solution. So for example, the forms usually just y, and then maybe some constant, and then plus the defined function. Well, maybe from x0 to x. So this is happen when the integral of g of t dt is non-elementary or non-elementary. Non-elementary means that we cannot express it in terms of elementary function, which is our regular functions that is in our calculus 1. Okay. Usually when you express this in your calculator, usually they will show error function or maybe error, usually. Depends. So it's the best we can do to show the solutions. Okay, just write y of x, y0 plus the integral defined functions. Okay? For example, we can try we have initial value. So this function here, this e with power of negative x squared, is non-elementary. So when we integral this e, we cannot do that actually. We cannot really have the expected results from this, but we still can solve the differential equation. So let's just try. So how to do this? First is using dummy variable. So the dummy variable is like when you did the fundamental theorem of calculus, you're introducing another variable like t, okay, just to help the calculation in the middle. Okay. So for example, we try to make with the 2 is from this initial value, and then we define as something some x and some x, and then we change the variables inside, becomes dt. And this will becomes y, or you can see that this is actually canceling from 2 to x. And the right part is just as it is. It is this integral defined function. So we just write this integral, the whole thing, and then dt. So we are going to have y of x minus y of 2 equal and we can just write the functions or the solution. Y of 2 is 6, so we can write this is 6 plus the whole thing here. So this is the best way we can come up for the solutions for the integral defined function, or for non-elementary, Okay. Well, that is actually the separable equations. Okay, so finish the sections. The other part, from the first order, we still have at least separable, linear, 1, 2, at least 4 methods in the first order. So this is the first one, the separable one. I should say the easiest one, Okay, I think I will just stop until here. We are going to have a feedback as usual. Okay. Let me check if I can make it through here. Usually, I don't know if I'm using the iPad. Sometimes they just keeps going out from the presentation. So if something happens, I will change to laptop. Okay, this is also because the roll call for attendance, I think, no longer available. So I have to find a way to check the attendance aside from the paper. I'm very lazy for paper, so I think this is the best way for attendance. Okay, I think we can start. Okay, we can start. Okay, let's start. It's just 3 questions. Yeah, 1 minute. 1 minute.
I can see the picture. Which one? It's blurry. Blurry? Okay, I'm just gonna guess.
Very sorry. Very sorry. So this is like this slope like this, and it goes here. It goes here. Oh, very sorry. I should draw larger. Just the quality of hands. But anyway, I will explain. But I think the easiest way is to find the horizontal, right? 0, right? And then you check with the equation. That's the first one. I think the easiest way to tackle this problem, finding the horizontal slope. Okay. Who is left side? Okay. Okay. Get ready. Yeah, I already explained. But remember, inside this has y squared. Okay? Is it just to say where it's true or not? So first thing you can do is check the positive negative. It's like a line number, but it's vertical. Okay. It's vertical. It's checking whether the graph is decreasing or decreasing. Yeah. No, I forgot the last one. I forgot the last question. What's the last question? Oh, yeah. I hope you can read the answer. So 420. So you need to answer in order. Answer in order. And just looking the arrow, I think, whether it goes away, come together, or they are going the same direction. Okay? Yeah, it's called face line, face portrait also. Name.
What? Is it Wednesday both and
Really?
stay?
Okay. So no one got. Let me check. Oh, yeah. Should be this. Okay. Let me check. Yeah, ready. Corrected. Okay, ready corrected. Yeah. Now. Oh. Now the student. Who's this one? Okay. Good job. Okay, write your student ID for your attendance, and if you would like also to give me suggestions. Okay. Okay, if you finish, then that will be our class for today. We are going to see you next Tuesday. We are going to move to another topic.